Hi guys. Today we're going to look at the concept of continuity, which is from section 2.5 in the textbook. Continuity is an important concept in calculus and in some further math classes like real analysis and complex analysis. So let's look at the informal concept first. Informally, a function is continuous if you can trace along the entire function without having to pick up your pencil. So it doesn't have any breaks or missing points or vertical asymptotes. So this first example here is continuous. So we can trace along the whole thing, and we never have any place where we have to pick up the pencil. We could either say that this graph is continuous, period, or we could say that it's continuous on minus infinity to infinity. Now this next example, shows the three different types of discontinuities we can run into. And they're called removable, jump, and infinite discontinuities. If you trace along the graph here, at this point there's a hole in the graph, a missing point. And that's a removable discontinuity. I also just call it a hole. Now if we continue along over here, we get to a vertical asymptote. And we had to pick up our pencil and then come back up here. So that's an infinite discontinuity. And then over here, we've got a place where the graph, looks like part of a piecewise function there. Where from one side we approach here, but then we have to jump down to this other part to continue. So that's a jump discontinuity. So I'm going to label these. This one is removable, this one is infinite, and this one is a jump discontinuity. And those are the three types of discontinuities you might encounter on problems in this class. So that's the informal concept. If you look at the formal definition just makes the idea of not having to pick up your pencil, it makes it a little more rigorous, and it does it in terms of limits. It says a function is continuous at a number a if the limit as x approaches a is equal to the function's value. So let's go back up to the first example and look at that. Let's just pick some value on the function. Let's pick this. It doesn't really matter which one we pick. This thing's continuous everywhere. But I'm picking one where it's easy to see what the x and y coordinates are. Let's see, this is 1, 2, 3, 4, 5, 6, and this is 2. So I can come up here and say f of 6 is 2. I'm gonna erase this dot. F of 6 is 2, and the limit as x approaches 6 of this function is also 2. Because you can get on here and you can trace along, and as you get close to x equals 6, from either side, y approaches 2. So we can kind of look at that and analyze at that point it's continuous. And that would be true for any other point that we pick anywhere along this graph. That would also work for any point we pick on this second graph, as long as it's not those three places where it becomes discontinuous. So look, I want to do two things. I want to go back and look at the definition, and then I want to come back up here, and at each one of these places I want to see what goes wrong with the definition to make it discontinuous. So the formal definition says that f of x is continuous at a if the limit as x goes to a of f of x is equal to f of a. And there are three things that this entails. F of x is defined, f of a is defined. The limit of the function as x approaches a exists, and both of those things are equal. So let's go back up to the that second example and see which of those three things goes wrong at each one of those places. So I'm going to erase these, and let's see, this is 2, this is 4, and this is 6. So if we look at x equals 2, f of 2 is not defined. So that's enough right there for us to say it's not continuous. Because we need to have f of 2 be defined, we need the limit to exist, and we need those two things to be equal. All right, at 4, what's going on there? Well, a couple of things. Before we do the limit, let's look at that. F of 4 is also undefined. Therefore, it's not continuous. All right, let's look at the limit too. That's enough right there for us to say it's not continuous, but let's look at the limit as well. If we look at the limit as x goes to 4 of this function, this limit does not exist. It's infinity from one side, negative infinity from the other side, and so overall does not exist. All right, and so they can't be equal to each other. All right, what about at x equals 6? I'm going to come down here and do that. At x equals 6, f of 6 is defined. F of 6, thanks to the solid dot here, is 1. But what about the limit? The limit as x goes to 6 of f of x equals, well, if you come over here, from one side, we're approaching positive 2. If we approach from the other side, we're approaching 1. So the two-sided limit does not exist. So since the limit doesn't exist, that's enough to tell us that it's not continuous. Now, I want to do one more thing here. Because on 2, what if we had another dot up here on the function? So if I change that function and I put a dot in there, then f of 2 would be defined. It would be defined as whatever that y-coordinate is. The limit would be defined as the y-coordinate of this point, but they wouldn't be equal. So even if we added this point to the graph, it would still be discontinuous there. And that's by the definition. If we wanted to use the informal thing, it's discontinuous here because in order to hit the whole function, I have to go up here, then go up to there and pick up my pencil to hit that point, and then come back down. All right, I'm going to erase this point. So a few facts here. Polynomials and sine and cosine are both continuous on minus infinity to infinity. Rational functions are discontinuous at their vertical asymptotes, but they're continuous everywhere else. And square root of x is continuous on 0 to infinity. You know, because the graph there looks like this. So there's no breaks or anything there. That kind of brings up the idea of one-sided continuity. Let's look at that. This isn't going to come up a lot, but you should be familiar with it. A function's continuous from the left if the left-sided limit satisfies this. And this is a typo. This should say f of a. And this should say f of a, not just a. So it's continuous from the left if the left-sided limit is satisfied, and it's continuous from the right if the right-handed limit is equal to f of a. So for this example here, This is a graph that I drew on Desmos, but it's not very, it's not a great graph because it doesn't show what's going on at the transition point. When x is equal to 0, that's here. So 2/3 x plus 2, that means that we've really got a filled-in circle here. We've got an open circle down here. So this graph we would say is continuous. Tell you what, instead of just writing that out, let me actually explain how I'm doing this. If we look at this, the limit as x goes to 0 from the left, f of x. Okay, we're approaching from the left, so that means we got 0. And if we're approaching from over here, we're looking at x is less than 0. So if x is less than 0, that means that we're using this top guy. So this is 0. And that makes good sense on the graph. If we approach 0 from the left, that's approaching from over here, that's along the x squared. If we look at the limit as x goes to 0 from the right of f of x, if we're approaching 0 from the right, then x is positive. So that's going to be this one. Plug in a 0 there, you get 2. Now, what is f of 0? Well, we've already worked that out. It's 2. So what we'd say is at 0, this function is it's continuous from which limit worked? The left or the right? Which limit was equal to the function value? The right one. So this function is continuous from the right at x equals 0. Like I say, one-sided continuity, it's not that important. It's not going to come up an awful lot, but you should be familiar with it. All right, I think we'll stop this video here.